Well, welcome again to my lecture on thermochemical processing of materials. In this lecture, I'm going to focus on the deviation from ideal behavior in mixing different chemical species together to make an alloy or to have a chemical reaction as in CVD, for example, chemical vapor deposition. So what we're going to do is we will look for ways to compute the chemical potential of any species I in a mixture, because the equilibrium of a mixture is determined by the fact that the chemical potential of the species in one phase is equal to the chemical potential of the same species in another phase. So the key is to compute the chemical potential, to be able to compute that for real systems. So what I'll do is I'm going to start this discussion by going back to writing down an equation for the chemical potential, and I'm going to write it for a constant temperature system. So I have to start from a VdP term for the change in the Gibbs free energy, and I add to this the amount due to mixing, and then I try to compute the VdP in real systems. So let's start doing that, and we will see that we're going to introduce some new concept equivalent to the concept of pressure, but for a real system it's a little bit more general, and it will introduce a concept called fugacity. I know it sounds kind of weird, but it is a term that is used in thermodynamics of systems. So we will learn about fugacity as kind of a generalization of pressure, and it will help us in fact determine the equilibrium in a mixture that is deviating from ideality. So let's first write down some of these equations. So here what I have is for non-ideal gas, we have first we will look at what we've done so far for the change in the Gibbs free energy of an ideal gas, and that now is very familiar to us, and that gives us the famous relationship that this is equal to RT dln of P. Now suppose that I have, instead of an ideal gas, I chose a real gas. So for a real gas, I have dg is equal to vdp, and therefore I need a relationship between v and p. And this relationship, a lot of times I can find this relationship if I know the equation of state of the gas. So I have to look for an equation of state that describes the relationship between the pressure and the volume at constant temperature. We know that this relationship is PV equals nRT for ideal gas. So what is the equivalent for a real gas? Well, the equivalent is going to be defined in terms of a function called the compressibility of the gas. And here's how it looks. So in this case, I have, for a real gas, I have P times V is equal to Z, which is generally a function of the pressure and the temperature, times RT for 1 mole. And Z is the compressibility function. So if we have an ideal gas, Z should be equal to 1. Otherwise, it would be different from 1. So this z here is going to look like so. If I plot, for example, the dependence of the pressure of z on the pressure P of the gas, then this dependence will give me 1 at very low pressures. This is usually in log scale, so you have, say, 10, 100 and some units, 1,000 and some units, and the pressure, compressibility usually decreases and increases again at high pressures. And this is given at a particular temperature T1. If you change to a temperature T2, then it becomes different. And therefore, I have a functional dependence of Z on the pressure. Okay, well, we can use this, in fact, to define the change in the Gibbs energy, and that's what we will do in a second here. So in this case, we can write for a real gas, dG is equal to VdP, which is equal to Z times RT over P dP, and this is equal to RT times Z times d ln of P. And now we have a relationship that is very similar to the case of the ideal gas. Remember, the ideal gas had RT d ln of P. So now we just, all of a sudden, we found that we have now a combination of the compressibility and d ln of P. So that's going to let us define by 3 lines, means definition, that this combination, we're going to combine it together and define a new parameter that's called F. And F is basically similar to the pressure. So if you look at this line for a real system and this line for an ideal system, they look exactly the same. However, the definition of F comes from equating d ln F to the amount that we have in the box, which is Z times d ln of P. So that's kind of where we are right now in terms of defining the properties of the system, and we are now trying to figure out if we can proceed with kind of knowledge of this fugacity F. We need to calculate the fugacity F. If we know F, then we would know the change in the Gibbs energy dG. So in order for us to do that, we can do it in 2 different ways, in fact. And I'm going to write down the 2 different ways. One way is if we know the relationship between the pressure and the volume, and that means that we know the compressibility function, some form of the compressibility function, then we would get a way to integrate and get the fugacity of the gas, F. Another way, if we have a liquid, for example, then how do we get the fugacity? We don't have pressure, compressibility data. Then the other recourse for us would be to use the basic definition of the fugacity, which I outlined in this equation, and use the thermodynamic data to calculate the Gibbs free energy. So on the one hand, we can calculate the Gibbs free energy. That gives us the fugacity. So these are the 2 different ways. I'm going to write them down, and I'm going to apply first to the case of a real gas where we know the compressibility function, And then I move on to the case of, say, a substance like water and steam. And in this case, I don't have equation of state, but I have thermodynamic data such as enthalpy and entropy. And from that, I can compute the Gibbs free energy. So let's first discuss the case of a real gas from which I have the compressibility function Z. So in this case, I have to define, so for the case of a real gas, I'm going to define the Fugacity coefficient. And the Fugacity coefficient is just a help to tell us how to compute the fugacity from the pressure. So if we define it in this fashion, then we are able to find the fugacity F, which is the final result we want, once we know the coefficient phi. So both of them kind of are equivalent definitions. So in order for us to find the fugacity coefficient, and hence the fugacity itself, then we're going to start talking about properties that are deviating from ideal. So we're going to define again here what we call residual properties. Residual properties. And the residual properties are those that are some deltas from the ideal case. So M residual is defined as M for a real system minus M for an ideal gas. So this kind of definition here, where M could be an entropy, an enthalpy, a free energy, etc., like that. So right now I'm going to look at this and try to compute the residual Gibbs free energy in this fashion. So what I'll be doing in the next is what I'll do next in here is that I'm going to, I know how to compute dG for an ideal gas, and then I'm going to use the equation of state for a real gas, and then I'm going to take the difference between these two to get the residual Gibbs free energy, which is the difference between the real minus the ideal. And that you will see is going to give us access to computation of the fugacity coefficient. So let's try to do that together right here. And as you can see here, I'm going to write dG residual is equal to dG minus dG of the ideal gas, and dG residual is RT, dG is RT d ln of F as we define it, minus for ideal gas is RT d ln of P. And using the law of logarithms, this will be d ln of F divided by P, and that is, from our definition, is RT d ln F of phi as we define it. So we have now, if we have now an element in I, to be specific, then this phi is for that element I, and this for a pure unmixed element I that we have in our system. So we will use this equation. So now if you look at this equation here, you will see that in this equation I'm going to have on the left hand side here of this equation, if you can see me right there, on the left hand side of this equation, I need to define or find the difference between the ideal and the real. And on the right side is what I want, which is the Fugacity coefficient. So I want to compute this, and I know this because I know the difference. So let's try to do this step right together here. So in this case, I have now the difference is going to give me this step, d ln of phi. So d ln of phi I is equal to d of g residual of I over RT. And I can pull the RT out, and dg residual is basically VdP, but V minus V ideal gas times dP. And this will give me the V is, if I take the V ideal gas as a common factor, if I just take it here as this is a common factor, ideal gas, then I have V over V ideal gas minus 1 dP. And the V ideal gas is RT over P. So give me RT over RT. And I get dP here, and then the P down here from the ideal gas. And then I have V over V ideal gas minus 1. This is basically the function Z minus 1. So I end up here is I'm going to end up with the Fugacity coefficient defined now finally as, in this equation, d ln of phi I is equal to Z of element I minus 1 d ln of P. So that is, now I can, if you think about it, at this point, I can actually integrate this equation up here. I can do the integration very easily. On the left side, it can give me phi from a reference point. On the right side, I can integrate it from any low pressure to a high pressure. The reference point we're going to choose is the ideal gas reference point. Where low pressure, all gases, real or not, they behave like ideal gases. So finally now I have this equation that I can do for finding phi in the system. So in this case, I have ln of phi I is equal to integral from 0 to P of Z minus 1 times d ln of P. And this will be my final equation that I can use in my system here to determine the Fugacity coefficient. So that's one way of finding the Fugacity coefficient if I know the compressibility data. So now you can ask yourself, what if I don't know the compressibility data? What if I just have a liquid? What if I have steam? Like in one of the homework assignments, we have steam. How do we calculate the Fugacity coefficient? And hence, how can we calculate the Fugacity itself? Well, remember that the Fugacity is linked to dg. So dg can be written as RT d ln of F. So if you integrate left side, you can get the G. Right side, you can get F. But you have to integrate from a reference state, and G is obtained from the thermodynamic data, which is H minus Ts. So let's follow this procedure and finish the lecture with this procedure. So let's have here the procedure, procedure that we follow. Let's kind of continue here on this page, and we write here an alternate route to compute fugacity. So this alternate way is that from the thermodynamic properties. So if I start from the basic definition of the fugacity, which is RT dln of Fi, I can integrate this. I can say that dln of Fi is equal to dgi over RT, and I integrate left and right from a star, which is a reference condition, to any current condition Fi here and Gi here. So I end up with an equation that says ln of Fi minus ln of Fi star equals to 1 over RT of Gi minus Gi star. So this is again another way to compute the fugacity of a substance once you know how to get the properties of that substance, meaning the Gi, which is Hi minus Tsi. So if we know this and this from the steam tables, for example, and we chose the reference conditions to be low pressure, for example, any low pressure, then we know the fugacity at very low pressure is the same as the pressure. Fugacity is the same as the pressure, provided that we have an ideal gas in this case. So to summarize the lecture, we're able now to compute the fugacity and the fugacity coefficient in real systems, either in a gas system that we have the compressibility data or the function z that describes it, and in the case of a liquid or a steam, for example, we can obtain the same data from the thermodynamics of the enthalpy and entropy and form the Gibbs energy, from which we can get the fugacity. And I think that will finish this lecture, and we'll continue to see what happens when we put things in solution in the next lecture.